So thank you very much, Professor Joslyn. Go ahead.
Yes, thank you for inviting me. I'm going to be talking about communicating climate change. And so this is a very, very big contrast from the previous talk where it was the very big picture. This is now narrowing it down to kind of a very small picture, because what I'm going to be talking about mainly is my own research program. So 90% of what I'll be talking about is my own research program. And so I like to begin by talking about what my perspective is. I am a cognitive psychologist, and so we focus on individual cognition, or how the mind works. My work in particular is on decision making, and I ask questions about how people make decisions under uncertainty, what communication better informs those decisions. And my work now is largely experimental, so I'll be talking today about a lot of experiments. But the questions that inspire my work come from the real world. So initially I started in the domain of weather and then moved into climate change. And I have some work there that I'll be talking about today. And we also have some new work on COVID-19. But the bottom line is that what we find is that people can understand fairly complex scientific information as long as it's presented in a way that aligns with how they process and represent it. So in the lecture today, I'll be starting out by talking about some of my work in the domain of weather, and then I'll move to work in the domain of climate change. So in the domain of weather, one of the first things that we were interested in was this issue of uncertainty information. So what I mean by that is something like a 30% chance of gale force winds. Turns out that experts are reluctant to give people, members of the public, non-experts, us, explicit numeric uncertainty estimates like this, because they fear that they will be misunderstood or misused. So instead, what we often get are categorical risk expressions like gale force winds are likely. And this is essentially what the American National Weather Service does with their watch and warning system. So a watch is conditions favorable for a weather event that might pose a risk to life and property, forecaster confidence around 50%. Advisory nuisance conditions, forecaster confidence 80%. Warning, risk to life and property, again, forecaster confidence of 80%. But when any of these are issued, just the word is used. They aren't accompanied by these definitions. And in fact, I had to dig pretty deeply into the American National Weather Service website to find them. Sometimes we are told what to do. So for instance, mandatory evacuation. And there have been problems with this system for some time. So there's an interesting analysis of the tornado season of 2008-2010 that found that residents within the warning polygon, that's this peach-colored thing on the map here, were no more likely to seek protection than those outside in the same county, about 40%. It's not a whole lot better with hurricane evacuation, 40 to 60%. So people began to wonder, why is compliance so low? So this is a very complex problem, and there are many reasons. Some people just don't have any place to go, others lack mobility. It turns out to be costly. But what we were interested in is whether or not there was a lack of trust in the forecast, because without the definition, these are presented as deterministic, implying that a tornado or a hurricane will happen in that area. And people know, as we learned early on in our research program, that weather forecasts involve uncertainty. So maybe they try and estimate it themselves, and they underestimate the likelihood. So there's been a debate for some time now about whether public weather forecasts should include more uncertainty information. On the pro side, there is more and more reliable uncertainty estimates available for many weather parameters. So in a sense, it would be more honest and accurate. It's the way the forecaster thinks about it. And it may be more plausible to users as well. In other words, it may inspire higher trust. It's definitely more information. Whether this is a good or a bad thing is an open question. But on the counter argument is that people may not be able to understand numeric estimates like this, and that may in turn make their decisions worse rather than better. So we set out to test that question. And here's an example of one of those experiments. This is a lab-based simulated road maintenance task. We bring university students into the lab, sit them in front of a computer, and they're playing what is essentially a computer game, but they're trying to decide whether to apply salt brine to the road to prevent icing. It has to be applied before freezing temperatures are reached. And so the decision is based on a forecast for nighttime low temperature. In order to motivate them, we give them a $36,000 virtual budget. The cost of treating the roads on a single day is $1,000, but they get penalized if temperatures fall below freezing and they have failed to salt the road, $6,000. So each day they get a temperature forecast for that night. And then after they make their decision, we tell them what happened. And they do this for 2 simulated months. It's about 60 trials, but it takes about 45 minutes to an hour. And then when they're all done, we give them a cash reward commensurate with their ending balance, about $1 per 1,000 in their virtual budget. So here's what an individual trial looks like. They've got the nighttime low temperature. These are all in Fahrenheit because this is a US sample, but I've translated it for you. And then they make a decision. They push one of these 2 buttons, whether or not they'd like to salt the road. This person is deciding to salt. And then we tell them what happened. So in this case, it actually reached freezing. So they avoided a penalty there. And by the way, these are real forecasts and outcomes that came from the historical records. So they don't always match up. And so in this experiment, there are 2 conditions. Half of people got what I'll refer to as a deterministic forecast because they got this single value implying that's exactly what's going to happen. And then the other half also got the probability of freezing. And what we find is that people have higher trust in the forecast and make better decisions when they also have the % chance of freezing. So we've seen this now in many experiments. That's just one example, but many different scenarios, different decisions, multiple alternatives and updates. Consistently, people make better decisions when the numeric likelihood is included, and they have greater trust in the forecast when the uncertainty is acknowledged. But these first studies were done on college undergraduates. So we began to worry, maybe those with less education and lower abilities wouldn't benefit. In fact, maybe it would make things worse for them. So we did a series of studies with online samples who had a broader range of abilities and backgrounds. And this is an example of one of those studies. It's called an individual differences study because we're looking at how people differ from one another. And the basic question for this research is, what are the abilities that are important for this road salt task? So we looked at education, and that's just what you might think it is. It's whether they had a high school degree, some college, advanced college degree. We also looked at numeracy, and this you can think of as the mathematical equivalent of literacy. We use a Berlin numeracy scale and has questions about ratios and statistical concepts. We also used a measure of working memory capacity, and this takes a little bit of background information. Working memory is one's ability to maintain and process information in consciousness. Cognitive psychologists think of people as having at least 2 kinds of memory. Long-term memory is what you usually think of as memory. So maybe it's your memory for your last international trip before the COVID lockdown, or what you had for breakfast this morning. Working memory is roughly synonymous with consciousness. So it's everything that you have, that you are aware of right now. So if you can do a subjective inventory of this, think about what are you thinking of right now, and hopefully you're thinking about what I'm saying and the images on my screen, but you may also be thinking about what you're going to have for lunch and a few other things. The point is, though, that while long-term memory, the capacity is very large, for working memory, we have a relatively small capacity, although there are individual differences. And it's important because this is where a lot of decision-making and problem-solving take place. So we thought it was important to measure that as well. So we used a common measure of working memory capacity called the reading span. And then the final thing we looked at was cognitive reflection. And to understand this, you have to understand that many cognitive psychologists think of humans as having 2 reasoning systems or processes. One is referred to as system one, although we don't think of it as a single biological system. System one is fast and automatic, largely unconscious in the sense that although you are often aware of the product of it, you don't know how you got there. It's based on associations rather than causal inferences and pattern matching, and I'll give an example of this in just a minute. System two is slow and deliberate, it's conscious, it uses up working memory capacity, it's rule-based, and it's analytical. And much of the time, these two systems work together, but sometimes they are in conflict. And that's what the cognitive reflection test is about. It's a bunch of trick questions in which you have to suppress an intuitive and automatic system one wrong answer in favor of a reflective and deliberative system two right answer. So here's an example. If it takes 5 machines 5 minutes to make 5 widgets, how long would it take 100 machines to make 100 widgets? And you can type your answer into the chat if you'd like. The automatic incorrect answer is 100 minutes. The deliberative correct answer is 5 minutes. But people really want to say 100 because pattern matching is a big deal for system one. So it goes 5, 5, 5. They want it to go 100, 100, 100. So these are the kinds of questions that are in the cognitive reflection test. So we wanted to know how this predicted performance on the road salt test, but what we really wanted to know was whether it differed depending on the kind of forecast we gave them. So a single value forecast versus the % chance of freezing. And we really thought that probabilistic forecast might require more education abilities because it's more information and it's more complex information. But this was just about the opposite to what we found. We found that in the deterministic condition with that single value forecast, more education and higher cognitive reflection scores led to better decisions. We found that people with higher numeracy made better decisions overall. And we found that none of these were predictive in the % chance condition. So we think that education and cognitive reflection is important in the deterministic condition because this is the condition in which people are left to assess the likelihood on their own. It's a task in which that likelihood is important, the likelihood of temperatures falling below freezing, but they don't have that information. And having higher education and higher cognitive reflection scores may help them do that. We think that higher numeracy help people to make better decisions overall because this is a task in which people tend to be risk-seeking. So they have only 2 options. They can pay out of their budget or they can risk getting a penalty. And in situations like that, people often would prefer to take the risk. So having higher numeracy may help them to appreciate the value of paying the long-run strategy. And we think none of these mattered in the % chance condition because abilities and education are least important when all the relevant information is provided to support decision makers. In other words, more is more. So there's an old adage when communicating with the public, keep it simple, less is more. But we're beginning to think with evidence like this that at least to a certain extent, more is more. So this line of research in the context of weather showed that numeric uncertainty estimates, people can understand them. They can't understand them on a theoretical level. In fact, we've asked questions that reveal that fact. They understand them more on a practical level. They can use them to make better decisions. Advanced education and abilities are not required for this advantage. And acknowledging uncertainty increases trust in the forecast. Okay, now I'm going to shift from research done in the domain of weather to research done in the domain of climate. And the first study I'll talk about here extends that advantage of uncertainty information to climate predictions. And then I'll talk about 2 studies about targeted explanations, and I'll explain what I mean by that in just a minute. A lot of this work is done with a former student of our previous speaker, Ann Bostrom, the Evans School of Public Policy at the University of Washington. So I said that one of the biggest advantages for uncertainty information in the context of weather was that it increased trust. And trust for climate change is a big issue. There's limited trust in environmental scientists. Only 47% of Democrats think what they're presenting as a fair and balanced picture, only 19% of Republicans. While 72% of Democrats think that climate change is largely human caused, as scientists tell us, only 22% of Republicans do, and only 20% of either group understand the huge degree of scientific consensus, and only 26% are very worried about it. So we began to wonder if this might have to do, at least in part, with how climate change is expressed. So an increase of 3 degrees centigrade by the end of this century. It implies great precision, and people know, we learned from our work with weather forecasts, that predictions like this involve uncertainty. So it might help to add an uncertainty estimate. It may increase trust, which may in turn increase concern. But the counter argument is that climate change is very different than weather, in part because it's very political. And so uncertainty estimates may be taken in this context by some as disagreement or lack of consensus, or incompetence on the part of climate scientists. In other words, it may have a boomerang effect for some. And this is predicted by the theory of motivated reasoning that says that people tend to process information in a manner that reinforces their prior beliefs or wishes. The other way that climate change is expressed that might make it hard to understand is that it's very abstract. It's hard to imagine what the impact of that global average increase will be on me. So it might be better to express this in concrete terms, such as the increase in heat waves. That way the impact may be more understandable, and that may translate into an increase in concern. So experiment 3 that I'll be talking about now tested these questions. Do uncertainty estimates increase trust, and do concrete predictions increase concern? So this experiment tested 4 expressions of the increase by the end of this century compared to last century. 2 of them are what I'll refer to as deterministic single value forecasts. And again, we translated this into Fahrenheit because this was a US sample, or 19 more heat wave days a year. And 2 of them included that information, but also a 90% predictive interval. And what I mean by a predictive interval, it's a range of values within which the observed value is expected with specified, in this case, 90% chance probability. And it's between 4 and 11 degrees and 5 and 48 days. This was a nationally representative US sample, and everyone was randomly assigned to one of these conditions. They only saw one of these expressions. So the first thing we looked at was trust, and this was a rating scale between completely and not at all. People who had the predictive interval, all the blue bars here, those who had the deterministic prediction are the black bars. The Republicans are on the left, Democrats are on the right, and the abstract version is on the left-hand side of both of those. And the first thing to notice is that Democrats expressed significantly higher trust than did Republicans. And this is actually true of all of the dependent measures that I'll be talking about with respect to this study. So I'm not going to mention it again, but you'll be able to see it in the bar charts. But importantly, people who had the predictive interval had significantly greater trust than did those who had the deterministic forecast. And this was especially true of Republicans who had the concrete expression. And this translated directly into increased concern. So on the y-axis now is a rating for concern between not at all and completely. And notice that Republicans have much greater concern when they have this expression. We also asked about understanding. How well do scientists understand the issues relevant to climate change? And that was because we worried that having the predictive interval might decrease the perception of competence. But in the context of Republicans here, they had significantly higher rating of scientists' understanding when they had the predictive interval than when they didn't. We also asked about scientific consensus because we were worried that expressions of uncertainty might reduce this perception. So how much agreement is there amongst climate scientists? about climate change, and they rate it between completely and no agreement. And again, Republicans who had the predictive interval rated greater agreement instead of less, what we feared might happen. So with this experiment, we've shown that uncertainty expressions inspire greater trust in climate as they do in weather forecasts. We have actually a number of studies showing the same thing. There are no boomerang effects. For no groups did probabilities reduce trust. And in fact, there's kind of an anti-boomerang effect in the sense that there is greater trust among Republicans when this predictive interval is included. I'm not saying that political ideology doesn't matter. It does. Democrats had greater trust and concern. Democrats rated scientists as having greater understanding and consensus. But for Republicans, this probabilistic concrete expression was particularly convincing. It increased trust, like it did with the larger group, but it also increased concern about climate change, perception of scientific consensus, and perception of climate scientists' understanding. So then we thought, let's try something else. So we moved on to climate change explanation. So this is a very complex issue. It's difficult to understand, but there is evidence suggesting that greater understanding tends to correspond with more concern. And there's new growing evidence that explanations increase understanding. So we wondered whether perhaps some explanations might also increase concern. The counter-argument, of course, is that knowledge deficits alone do not account for attitudes toward climate change. There are big effects of political ideology. So explanations might backfire because of motivated reasoning. Any explanation might just reinforce the person's previously held views. In other words, there might be a boomerang effect here. But as I said earlier, there is a new growing research showing that causal explanations help, especially from the work of Rani and colleagues. Explanations increase understanding in the causal mechanisms that lead to global warming. Here's an example of one of his explanations. These are all can be seen on his website, how global warming works. This is one of the shorter explanations. It says that Earth emits absorbed light's energy as infrared light. Greenhouse gases absorb those. By increasing the amount of greenhouse gases in the atmosphere, humans are increasing the atmosphere's absorption of infrared light, thereby warming Earth and disrupting global patterns. And this explanation and many others has shown to increase acceptance in climate change with no boomerang effects across the political spectrum. So what we were interested in was this delay explanation. We thought that perhaps people don't understand the urgency of the situation, and there is some evidence that many people hold a wait and see attitude. Let's wait until we see it's really a problem before we do anything that has economic consequences. And this suggests that they're assuming that there will be a quick fix, that as soon as we start reducing emissions, there'll be a reduction of CO2 in the atmosphere. But in fact, the delay is very long between the reduction of emissions and the reduction of CO2 in the atmosphere, on the order of hundreds of years. So we wondered if people understood this, maybe they'd have a greater sense of urgency. So we used this delay explanation. We said, if we start reducing greenhouse gas emissions today and reduce them every year, concentrations in the atmosphere will continue to rise for 100 years, global average temperature for 200 years, and only fall after 300 years. Turns out that this kind of relationship is very difficult for people to conceptualize because of the difference in patterns. Emissions are falling at the same time concentrations in the atmosphere are continuing to rise. And people really want patterns like this to match. So they use a simplifying assumption. They assume that causally related changes are occurring together, both in the same direction, therefore we can afford to wait and see. But CO2 is removed from the atmosphere very, very slowly, so concentrations will continue to rise for a long time. So in other words, people have an inaccurate mental model of this relationship. So what I mean by a mental model is a cognitive representation of something that cannot be apprehended with our senses. So we all have a mental model of the solar system, for instance, the relationship of the sun to the other planets. So we build a working model representation of this and evaluate it in our minds in consciousness. And it includes things like the relationships between the components and the mechanisms of how they interact. But mental models change as we learn new things about phenomenon. One of my favorite examples is this one. It's children learning that the earth is round, and they have to incorporate that with their perceptual experience of the flatness of the earth to build a mental model that incorporates both of those. So some kids have this model. It's kind of a disc. It's round, but it's not spherical. Some kids have a hollow sphere with a disc inside. Some of them give us a little opening at the top to breathe out of. Some have this flattened sphere version, and then eventually they have the adult version of the spherical earth. So the point is that mental models change as you learn things. So people have this erroneous mental model of the relationship between emissions and concentrations. And this is a common error that's been noted before in the context of business and economics called the stock flow problem. People assume that production matches accumulation, ignoring distribution. So the insight is that stock accumulates if the inflow, the production, exceeds the outflow distribution. Sometimes this bathtub analogy helps. So you tell people that if the water's going into the bathtub faster than it's draining out the bottom, then the bathtub is going to overflow. But we went straight for the pattern itself and told them these patterns don't match. The actual numbers here are based on a number of assumptions. We thank Naomi Goldenstern for having calculated this for us, but regardless of the assumptions or the exact numbers, the pattern is the same. Emissions will have to fall for a long time before accumulations and temperatures, while accumulation and temperature continue to rise. So in this experiment, there were 3 conditions. We gave some people no explanation at all. It was the control group. We gave some people the basic explanation that came from the Rand and Clark work about the effects of greenhouse gases. And we gave some people that basic explanation and the delay explanation that I just showed you. And again, this was a nationally representative US sample. And participants, excuse me, were randomly assigned to one of these 3 conditions. And then we asked them a series of questions. So we asked them, for instance, how long will concentrations of greenhouse gases in the atmosphere continue to rise? The correct answer is 100 years. I've underlined it for you, but of course not for participants. And this can be answered by just repeating back the information in the explanation. And we really wanted to know if the explanation changed how they think about this issue, their mental models. So we asked them how much they agreed with this statement. Until we're sure that global warming is really a problem, we should not take any steps that would have any economic costs. I'll refer to this as the wait and see strategy. Okay, so here's their answer to the factual question, how long will concentrations continue to rise? Percent of respondents is on the y-axis. The answers they chose are on the x-axis. The correct answer is 100 years. People with the delay explanation are the yellow bars, and I've stacked liberals on top of moderates on top of conservatives, so you can see there's not much actual difference here. But those with the delay explanation were significantly more likely to get the correct answer. And people tended to answer with a much shorter time period. And there's no difference by political ideology. So here's the wait and see strategy. So remember, less agreement is better for this. Less agreement indicates greater urgency. Again, the delay, those who have the delay explanation are the yellow bar. And here, there's a significant effect of political ideology. Liberals agree least, as you might expect, and conservatives most. But among conservatives, those who have the delay explanation agree less, significantly less. So with this simple delay explanation, we taught participants something new. Many of them answered correctly when they had the information. And it was true across political ideology groups. And with this delay explanation, conservatives were less willing to endorse a wait and see strategy, suggesting they're not just parroting back the information that we gave them, but rather that it changed their mental model and their attitudes toward climate change. So then we began to wonder, what about other misunderstandings? Could we have the same effect with simple explanations on those? So this is actually brand new work. It has not yet been published, hot off the presses. We actually ran it during the pandemic. This has to do with what I'll refer to as the pollution confusion. So global warming is often viewed as common air pollution, and this prevents people from identifying effective means to combat climate change. And it may also reduce a sense of urgency because people may assume that greenhouse gases can be eliminated as quickly and easily as can other kinds of pollution. So pointing out the differences may help people to appreciate the distinction and improve their mental models. And it might also help them to identify effective strategies. So experiment 5 tested this question. So this time what we showed them was a comparison table presented on the screen, one segment at a time. So we started off with the sources and we told them, you're right, air pollution and CO2 are similar in the sense that they come from similar sources, burning fossil fuels. But they're different in many respects in terms of where they go, their sinks. Most air pollutants are removed by fast reactions with other chemicals, etc., whereas CO2 is absorbed by ocean, captured by forest very slowly. Air pollution can reflect incoming ultraviolet light, whereas CO2 retains infrared light, leading to global warming. And the impacts on humans are different. Air pollution, respiratory diseases and cancers, CO2, more long-range heat stress, undernutrition, etc. So in experiment 5, again, there were 3 conditions. Some people got a no explanation control. Some people got the basic explanation that came from the Rennie and Clark work. And some people also, in addition to that basic explanation, got the comparison table. But we also reran that delay explanation. So I'll refer to these as 6A and 6B, or it should be 5A and 5B. Sorry, my dog is here. Then we asked a series of questions. We asked, which of the following health consequences is a health consequence of CO2? It was a multiple choice. Heat stress is the correct answer. This can be answered from the pollution comparison table. We expected people who had that to answer correctly more often. This one asks the question before, in the study before, if we start reducing CO2 emissions today and reduce them every year, how long will it take? Correct answer is 100 years. And this can be answered by the delay explanation. So we expected people in that condition to answer correctly more often. But again, both of these can be answered by simply repeating back what was in the information in the explanation. And what we really wanted to know was whether the explanation changed how people think about the issue, changed their mental models. So we also asked these strategy questions. We asked them to rate their agreement with this idea, reducing air pollution is key to reversing global warming. And we expected people with the pollution comparison table to agree less with this because less agreement suggests better understanding. We also asked, until we're sure that global warming is really a problem, we should not take any steps that would have economic consequences. And we expected people with a delay explanation to agree less with this because less agreement suggests better understanding. So again, there were 4 conditions: no explanation, the base, the pollution comparison table, and the delay explanation. And then everybody got the same set of factual questions and the same set of strategy questions. So this is the pollution comparison condition and their answer to the factual question, which of the following is the health consequences. So this is the proportion accurate on the y-axis, liberals on the left, conservatives on the right. And those who have that pollution comparison table are the black bars. The base and the no information are the gray and the white bars. And as we predicted, people with the comparison table answer correctly more often. So then we went on to look at the strategy question. Reducing air pollution is key to reversing global warming. Remember, for this one, less agreement is better because this is an ineffective strategy. And here there was a main effect of political ideology, but it's actually in a kind of different direction than you usually see. Here, liberals are agreeing most and conservatives, well, moderates least. But liberals and moderates who had the pollution comparison table, the black bar, agree significantly less than others. Okay, so now we're moving on and we're looking at the people who had the delay explanation. That's the yellow bar. Proportion accurate is on the y-axis. Liberals are on the left, conservatives on the right. And again, those with the delay explanation answer correctly far more often than those who don't have the information. Here, there's no effect of political ideology. So this is the strategy question with the delay manipulation. Those who have the delay are in the yellow bars. And notice that there is, again, effect of political ideology with conservatives agreeing the most, less agreement is better here, and liberals the least. But those who have the delay explanation agree significantly less with this strategy. So what we found is that these simple explanations increase accuracy of factual questions about the information presented, decrease agreement with ineffective strategies, suggesting a deeper understanding. And these effects are seen across the political spectrum. There's one more thing I want to tell you about, though. This was unanticipated, and I'm referring to it as crossover effects. So remember that we asked all the questions after each explanation. So people with the pollution comparison table got the pollution factual question, but also the delay factual question, the pollution strategy question, but also the delay strategy question. And the same was true of the delay explanation. They got the delay factual question, but also the pollution factual question. And what we found here was that people who had the pollution comparison table actually answered the delay factual question more accurately and agreed less with the ineffective delay strategy. Similarly, people with the delay explanation answered the pollution factual question better. So, as I said before, we've shown with these simple explanations that it increases accuracy in factual questions, decreases agreement with ineffective strategies. The effects are seen across the political spectrum. And we believe that this new knowledge is actually interconnected, allowing people to answer questions that were not actually directed at that manipulation. Okay, so here's the take-home message. I think that people are capable of understanding much more complex issues than those for which they're often given credit. Much of the climate science that reaches the public today is vastly simplified. So we think that if climate communication was designed to include more complete scientific information, but targeting the cognitive processes and mental models of the recipient, that we'd see larger cumulative changes in trust, understanding, and appreciation of the urgency of these issues across the political spectrum. In other words, more is more. So that's all I have, except I want to thank all of the graduate students and postdocs who worked on this, and that's the end.